Hey guys, I had a request from a person on Facebook for the explanation for how scientists know approximately um, how far away the stars are, and I don't think it's a stupid question. I really think it's pretty fundamental um, to how the universe works and all that. So okay, this goes back to some basic trigonometry. You have your triangle, you have an angle theta. You have an x, you have a y. And what I know is, from definition, that tangent of theta is going to equal y over x. Okay? And so, let's say I have an x distance, and for the sake of simplicity, I'll call this side of the triangle equal to 1 meter. And I know that theta is like 54 degrees. And I want to know how far away this point is from my base, my x base, okay? If that's a 54 degrees. So what I have here is I have the tangent of 54 is equal to y over 1 meter. So tangent of 54 is equal to y in meters. Okay? So knowing this, I can go on to the explanation for basically a rough estimate for how back in the day people figured out how far the Earth was from the stars. I mean, now I can just, go to a computer, measure the wavelength difference of light, and I'll know exactly how far a star is away from the Earth. But back in the day it wasn't so simple. So we'll do this old school. Like, I'm not sure why I can't grab it, but it's not working. But at any rate, you have your sun, you have your Earth, and you have this distance from the sun to the Earth. Now, under very specific, very precise experiments, we have derived the speed of light as being approximately 300 million meters a second. Okay, I rounded up from 289 something, but that's approximately how fast the speed of light is. Anyone can measure the speed of light. Just perform a couple of experiments for yourself if you don't believe me, but that's how it works. Okay, so I know that if it takes 7 minutes for the light to reach me from the sun, then I know the distance the Earth is from the sun, and I'm going to use this as my x base for my base of my triangle. Okay. Now, looking at this from another way, I've got my axes: my y-axis, my x-axis, my z-axis, and this is in 3 dimensions. Okay. And we're going to say the sun is at the center of these two, and my Earth. And I've already established a base. Okay. Now, if I was trying to find a star in the sky, how far it was, like I said, you can measure its wavelength and the shift in the changes of its wavelength, and you'll know approximately how far away it is. But there's another way. Back in the day, and they still use this method. Say I have a star in the sky, and this, because I know the distance from the Earth to the sun, that's going to make a certain degree base with my sun, and then using the tangent, like we did, this is my y side and this is my x side. This is my my hypotenuse. I know that tangent theta is equal to y over x. Therefore, the distance the Earth is from this star is equal to x. Tangent theta is equal to y. A little bit more complicated than that, but I'll explain. Okay, so because here's the Earth, and I'm some point on it, I'm looking up at the sky, and I've got this radius of the Earth. If But I'm looking up into the sky at a star. Okay, so here I am, this little guy. Here's my horizon, and I'm looking up at this star. And it's making a degree angle theta with the star. So really I'm getting this angle. From this angle I can derive this from this angle, and knowing how far the radius of the Earth, that makes this long triangle, and from that I can find the radius, the degree angle between the sun and the star and the Earth. Okay. And from that alone I can approximate how far away the star is, but it's not a good enough approximation. For the sake of science, we wait the whole 6 months and from the summertime to the winter time, and now the Earth is at a different distance from the sun. Okay? But also, the star has fell in the sky just a little bit. It makes a new degree, and we'll call this degree psi. Okay? From the Earth. From the Earth it makes a new degree angle. But I do calculations again, and I figure out approximately how far the hypotenuse is from the star, and I make a rough average between the two. Obviously scientists do this every, day throughout the year. If they're good scientists, they do this every day throughout the year to get a better, even more precise average for how far the star is away from the Earth. But that's basically how you do it, just using basic trig. And using the sun as a reference point for your base of the hypotenuse, and the Earth's radius itself as your second base of the hypotenuse for your second angle. But that's, not very intuitive to do this, and it took 1,000 years just for scientists like Galileo to decide that the Earth was going in an elliptical orbit, because they would look up in the sky and they would see the planets move across the sky like little zigzags. And they didn't understand why they did the zigzag pattern in the sky, because stars always move up a little bit and down a little bit, move back and forth. But you have these planets swish across the sky in these radically different trajectories across the horizon, and there was no accounting for it, so they decided that it must have been that the only way to explain these zigzag patterns that these planets do across the sky was to say that the Earth was orbiting around the sun. Okay, and through that leap of faith and through mathematics to prove it, they derived how far, the exact trajectories of the planets and everything, using a very painstaking process. They did this. So that's how we know the Earth revolved around the sun. Nowadays we can just go up with a little spaceship and see that the Earth revolves around the sun, and empirically know that it does. But that's how they did it back in the day. And from this, methodology, we come to this methodology where we can actually measure how far away the stars are, and you really can't mock scientists, okay? If you don't believe this, just go out with a telescope, do the measurements yourself, because, but what you come up with is that the stars are billions of miles away. Billions and billions. They're so far away that even going at light speed, it would take me millions of years to get to them, okay? So that's how we know that the light that reaches the Earth is millions of years old. It has to be. So you're really looking back in time at the stars. But that's kind of how scientists know that stars are so far away from the Earth. That's also why the Earth is not 6,000 years old. I know this is going to tread on some people's territory over here, but it just can't happen. There's no way of explaining how the stars are in the sky, and there's just no way that you can't do it with math. You can't do it. If you decide that the Earth is 6,000 years old, you're blind to the stars that are above your head, at night. But that's pretty much all for that debate. Check you later, guys. I hope I explained it. It's basically a simple trigonometry, a very painstakingly trig process. Over the course of a year, people know how far away the star is. Peace out, guys.